The next thing that I can talk about is independent samples t-test. This is the second kind of t-test we'll be talking about here. And this is one that's more commonly used than the one sample t-test just because it tends to be more relevant for the kinds of hypotheses that we have in psychology. One sample t-tests are useful tests, but they're not relevant all that often just because of the kinds of things that they address don't tend to be all that often what we're trying to investigate. So one sample t-test is a very, very common test that we want to undertake. So the independent samples t-test, generally speaking, it's relatively similar to the one sample t-test just because all the t-tests are doing a similar kind of thing. But what it's doing is it's comparing the mean score on some numeric variable between two independent groups. And we want to see if there's a difference in the mean score between those two groups. Do the two groups have approximately the same mean score or do they have a different mean score? It's also called a two-sample t-test or a between groups t-test. So all of those things are representing the same thing. The null hypothesis for our independent samples t-test can be written one of two ways. On the left-hand side, that's the first way of expressing the null hypothesis, which is that mu1 is equal to mu2. Mu1 being the mean score for group 1 and mu2 being the mean score for group 2. So if the two mean scores are equal, that would be our null hypothesis. The other way of expressing that exact same thing is just using a little bit of algebra to say that the difference between the two mean scores is equal to 0. So hopefully you can see that mu1 equals mu2 is exactly the same mathematically as saying mu1 minus mu2 equals 0. It's the exact same thing. We're representing the same thing here. And those are two equivalent ways of representing the null hypothesis. The alternate hypothesis, again, can be represented one of two ways. On the left-hand side, we're saying that the mean score for group 1 is not equal to the mean score for group 2. And on the right-hand side, we're saying the difference between the mean score for group 1 and group 2 is not equal to 0. So that's our null hypothesis, and that's our alternate hypothesis. As I said before, there's always assumptions that go along with every test, and assumptions are just certain conditions, certain criteria that need to be met in order for the test to be an appropriate test to run in this particular context. So we've got four assumptions for an independent samples t-test. The first one is that our dependent variables, we've got two variables for a t-test. We've got an independent variable and a dependent variable. The dependent variable, which is our outcome variable, has to be on some kind of numeric scale. Our second assumption is that the dependent variable is normally distributed in the population within our two groups. So the distribution of our dependent variable for group 1 is normal. The distribution of our dependent variable for group 2 is normal. The third assumption is that there's approximately equal variation or spread of scores between our two groups. And the fourth one is that observations are independent. So all of our data points come from separate people, from independent people, both within each of the groups, but also between the two groups, that the two groups are separate groups, are independent groups. We'll test those particular assumptions in a second, but let's talk about the research context for this example. So again, this is a different example from the previous one. This is the context of organizational psychology, this one. And what we're looking at here is whether the modality of communication can affect a person's perception of skill. Modality being how the information is actually communicated, whether it's through verbal speech or whether it's through written words. So does verbal speech contain extra information that can communicate skill or intelligence beyond just the content of the words that are spoken themselves? Our study design is an experiment, and particularly it's a between subjects manipulation, and that's necessary for the independent samples t-test because the groups that we're comparing have to be independent groups, and that's what they are in a between subjects manipulation. Our particular research question here is whether a person is more likely to be hired for a job, more likely to get a job, after giving a short speech describing their skills, or after writing the equivalent of a speech and having the employer read those words. So is there a difference in their likelihood of being hired depending on whether they spoke the words or whether the words were just read, whether they were written words that were read? And the hypothesis is that the speech is going to be more effective, that the person's speech itself, because it's comprised of vocal tone, cadence, and pitch that are integral to the speech, would communicate more information about their intellect over and above what's communicated in the actual content of the words themselves, even if it's the same words as the speech. So we've got two key variables here, and every independent samples t-test is going to have two variables. Our outcome variable, our dependent variable, which is a numeric variable, which here is the rating of somebody's intellect. And our independent variable, which is our grouping variable, which has two levels or two conditions. It's a categorical variable. And in this instance, that variable is a condition, whether it's a transcript condition, whether it's just the written words that are read, versus the audio condition, the actual hearing of the speech itself. And that's the citation for the paper that we're using the data from. So this is the data as it actually looks. So you can see that I've given you the syntax on the left-hand side there to pull up the data, again using the same process that I talked about for the previous one. And there's a whole lot of variables in this data set, but only two of which are relevant to our particular independent samples t-test here. We've got our grouping variable, which is condition, which has two levels, audio or transcript. And we have our intellect rating variable, which is a numeric variable, which you can see ranges, I think, from 0 to 10 or 1 to 10 or something like that. So two variables that are relevant for our independent samples t-test here. Going back to our assumptions, our first one is that, going back to our assumptions here, so our DV is on a numeric scale. We can tell that just by looking at the data. And we know that our observations are independent both within and between groups because that's a product of the actual design of the study itself. But the other two are things that we need to measure, that we need to actually test by looking at the data, because we can't tell if those other two assumptions are met, the normal distribution and the equality of variances, until we actually look at the data itself. So the first thing we can do is just to summarize the data. The first table up the top there is a summary of the overall average scores for this variable for the entire sample, and that's at 39 observations in this particular study. So we can see the overall average intellect rating score is 4.7 out of 10 with a standard deviation of 2. And you can see that the lowest intellect rating somebody got was 0.6, less than 1, and the highest is 9. But we can also have a look at the ratings between the two different groups. So the second table here is just using some other syntax to get a summary descriptive statistics table for each of the groups separately. So the top one here is the summary of our intellect rating for the transcript group. And then secondly, the summary of our intellect rating for the audio group. And what you can see here is that we do have a difference between the mean scores. So you can see that just by looking at the descriptive statistics, the audio group had a higher rating intellect score than the transcript group, 5.6 versus 3.6, so it was about 2 points higher. We can see that we've got 18 and 21 observations in each of those groups respectively. But what we need to do in terms of the t-test itself is to test to see whether the difference between these two groups is substantial enough and systematic enough for it to likely reflect a real effect in the population. And that's the whole point of conducting a hypothesis test, a formal hypothesis test, beyond just looking at the two mean scores and seeing that they differ. We need the hypothesis test to make an inference back to a population beyond just the sample data itself. So those are our numeric descriptive statistics. We can also look at a graph for the distribution of our DV between our two different groups. Here's the syntax to do that up the top there. And you can see we've got two different histograms, one for each of our groups. And this is representing just the same thing that the numeric data did on the previous slide. It's just slightly easier to see it often in a graph. So you can see that for both of our groups, we've got a range of intellect rating scores, but that the bulk of the data, the kind of middle part of the data in the audio condition is higher than the bulk of the data, the middle part of the data in the transcript condition. The next graph that we're looking at here is representing the same data, but what this data can do for us is to overlay the two graphs one on top of each other. So the green bars are representing the data from the transcript condition, and the sort of see-through white bars are representing the data from the audio condition. And so this just gives you a slightly clearer understanding compared to that graph of looking at the difference in the average scores. You can see that the average score for audio is higher than the average score for transcript. But also looking at the amount of overlap there is between the two distributions. So obviously we know that just by looking at the descriptive statistics, that there are higher scores in the audio condition than the transcript condition on average. But we also know that there's overlap. So not everybody in the audio condition got rated more highly on intellect compared to the transcript condition. And this is just representing the variability or kind of the messiness in the data that kind of justifies our need to use the t-test or the formal hypothesis testing to see if on average there is a difference between the groups in the population from which our sample was drawn. The next thing I'm going to talk about is one of the tests that we can use for one of our assumptions. So one of our assumptions for the independent samples t-test is that the variability or the spread of scores between the two groups is the same. And we can use a particular test called Levene's test for equality of variance, to actually formally test this hypothesis, to test this assumption, to see if the spread of scores is approximately equal between the two groups in terms of the population from which our sample was drawn. So on the left here, you can see just the graphs that we had on the previous couple of slides, and then on the right, we have the descriptive statistics. And by looking at the standard deviation, and we know that the standard deviation is a measure of variability or spread or dispersion of scores, we can see that the standard deviations are about the same between the two. So the transcript group has a standard deviation of 1.9. The audio group has a standard deviation of 1.6. So we can see that they are relatively similar. The transcript group has a slightly higher variation, more variation than the audio group. So what Levene's test can do for us is to see if this is a substantial difference between the spread of scores, the variability of scores, or whether they're approximately even. So how we can get started to do Levene's test for us, if we're using the menu system, we go up to statistics, summaries, tables and tests, classical tests of hypotheses, and then the one down the bottom here, which is the robust equal variance test. That's where Levene's test is located. And that brings up this menu, and the variable that we select at the top here is our dependent variable, our numeric variable, which here is intellect rating. The group variable is the one that represents the different or independent groups that our observations fall into. And for our purposes, it's the condition variable. If we were doing the same thing using syntax, using the written command, then the command name is robvar, robust variance, ROBVAR. And then we list our outcome variable, our dependent variable, comma, by, and then open parentheses, our group variable name, condition, close parentheses. And that gives us this output here. And you can see up the top of the output is some descriptive statistic information, this information here, and this is just the same as what was on the previous slide. And then the first row is the information that we read across for Levene's test. Ignore the W50 and the W10. It's the first row that we're reading across. The actual Levene's statistic itself is the first thing here, 0.89, with certain degrees of freedom. And then the p-value here is 0.35. And for Levene's test, the null hypothesis is that the group variances are equal in the population. So the null hypothesis is that the variances are equal. So what we want here in order for this assumption to be met is a non-significant result, by which I mean a p-value bigger than 0.05. And what we've got here is a p-value of 0.35, which is definitely bigger than 0.05, which means that we have a non-significant result, which means that assumption is met. So to recheck our assumptions here, we know that our DV is on a numeric scale. We can check that just by looking at the data itself. By looking at the descriptives, we could see that the DV was normally distributed within the two groups, and that was just by looking at the numeric and also the graphical descriptive statistics. In a couple of weeks' time, I'll show you a more formal test of normality, but just for today, we're satisfied just by looking at the graph itself and saying that the distributions are approximately normally distributed. We did Levene's test to test the assumption of the equality of variances, and we know by our sampling design that our observations are independent. So now we can actually formally proceed to do our t-test.